Hi, Stu Schwartz from MasterMathMentor.com. This is video BC10. The topic is polar coordinates and graphs. It covers the BC manual, pages 51 through 53.
All of the math you have learned so far is based upon the Cartesian or rectangular coordinate system that specifies each point uniquely as the signed distances to the point from two perpendicular lines called the x and y axes. The invention of the Cartesian coordinate system in the 17th century by René Descartes provides a link between geometry and algebra. For example, a circle of radius 3 centered at the origin may be described by all points whose x and y coordinates satisfy the equation x squared plus y squared equals 9. Many cities are based upon the Cartesian coordinate system. For instance, the city of Philadelphia is based upon the system with its two main streets, Market Street and Broad Street, as the x and y axes, with City Hall directly in the center. And streets form a grid about those axes. Bonaventura Cavalieri introduced the concept of the polar coordinate system in the mid-17th century. This system is based on a circular model. To form the polar coordinate system, we start with a point O called the pole or the origin. Each point P in the plane is assigned polar coordinates r theta as follows. R is the directed distance from O to P, and theta is the directed angle measured counterclockwise from the polar axis, the line theta equals 0, to the segment OP. Theta can be measured in degrees or radians, although for calculus purposes we usually use radians. The city of Paris is modeled on the polar coordinate system with the Arc de Triomphe as the center. Realize, though, that points are merely locations no matter what system we use to name them. So we can superimpose our Cartesian system over our polar system and realize that we can name the points using each system. The origin and any point along the positive x-axis are the only points that have the same name in both systems. The Cartesian point 4, 0, shown in red, is the point 4, 0 degrees in polar coordinates.
The easiest way to identify point A in the polar graph is 330 degrees. We could also write it as 3 negative 330 degrees if we choose our angle going clockwise rather than counterclockwise. We can also think of it as a radius of negative 3 along the angle of 210 degrees, or negative 3 along the angle of negative 150 degrees. However, 330 degrees is the easiest way to identify it. We can also change these to radians, so it would be 3 pi over 6, 3 negative 11 pi over 6, negative 3 7 pi over 6, or negative 3 negative 5 pi over 6. There are an infinite number of ways to identify the angle if we go around the clock more than once. The easiest way to identify point B is 2 180 degrees or 2 pi. Other ways to represent the point are shown. Point C, 5 225 degrees or 5 pi over 4. Other ways to represent it using angles that are negative or radii that are negative are shown. Finally, point D is easiest identified as 1.5 300 degrees or 1.55 pi over 3. Again, other ways to represent it with negative angles or negative radii are illustrated. Let us choose some arbitrary point P. We label it with the rectangular coordinates x, y, or the polar coordinates r, theta. We draw the right triangle to the point with horizontal x, vertical y, and the distance from the origin to the point we will call r. The angle created with the x-axis is theta. So there is a relationship between x and y and r of theta. If we want to go from polar to rectangular, we are given r and theta, and x will be r cosine theta and y will be r sine theta. If we have the point in rectangular and we want to change it to polar form, we are given the point xy, and r will be the square root of x squared plus y squared, and theta will be the inverse tangent of y over x. In 5, we are given the points in polar form and wish to change them to Cartesian or rectangular form. In A, the point is 5 pi, so x is equal to 5 cosine pi, and y is equal to 5 sine pi, and the point is negative 5, 0. In B, our polar point is 2 square root of 3 pi over 6. X is 2 square root of 3 cosine pi over 6, y is 2 square root of 3 sine pi over 6, and our point is 3 square root of 3. In C, our point is 8 5 pi over 4. X is 8 cosine 5 pi over 4, y is 8 sine pi 5 pi over 4, and our answer is negative 4 root 2, negative 4 root 2. In 6, we are given the points in Cartesian or rectangular form and wish to change them to polar form. When we go from Cartesian or rectangular to polar, we must be careful in calculating the angle. For A, our point is 3, negative 3. R is the square root of 9 plus 9, which is 3 square root of 2. Theta is the inverse tangent of negative 3 over 3, which is the inverse tangent of negative 1. The angle whose tangent is negative 1 is either 3 pi over 4 or 7 pi over 4. We have to be smart enough that we want the angle in the fourth quadrant, which is 7 pi over 4. So our point is 3 square root of 2, 7 pi over 4. In B, our point is 0, negative 2. R is the square root of 0 plus 4, which is 2. Theta is the inverse tangent of negative 2 over 0, which is undefined. The tangent function is undefined at either 90 degrees or 270 degrees. We have to be smart enough that we want the 270 degrees or 3 pi over 2. So our angle in polar form is 2, 3 pi over 2. In C, our point is negative 4, 4 root 3. R is the square root of 16 plus 48, which is 8. Theta is the inverse tangent of 4 root 3 over negative 4. Our answer to that is either 2 pi over 3 or 5 pi over 3. We must be smart enough to realize that this is a second quadrant angle, and therefore the angle is 2 pi over 3. So our polar form is 8, 2 pi over 3. Since points can be written in both rectangular and polar format, we can also write equations using both formats. Graphs that are linear are best written in rectangular form, while graphs that have curves are best written in polar form. For example, on the screen we see the red line, which is much easier written with a rectangular equation, and we see the blue rose curve that is much easier written with a polar equation. Non-functions with loops are very difficult to write in rectangular form and usually need to be written as a piecewise function, while in many cases, as we see in the blue curve, they are very easily written in polar form. Changing from rectangular form to polar form is not that difficult, even though the polar form is a little bit more complex. The simple y equals 2x plus 1 in rectangular form becomes r equals 1 over 2 cosine theta plus sine theta in polar form. The parabola y equals 2x squared in rectangular form becomes r equals sine theta over 4 cosine squared theta. But changing from polar to rectangular is a different story. Sometimes it cannot even be done, and when it can, the equation gets very complex and very difficult, if impossible, to solve for y. For instance, the very simple r equals theta becomes in rectangular form x squared plus y squared equals the inverse tangent of y over x squared. The simple r equals sine of 2 theta becomes, in rectangular form, the quantity x squared plus y squared raised to the 3/2 is equal to plus or minus 2xy. In both cases, it is impossible to solve for y. To convert from one form to another, we use the same relationships we saw previously. For example, we know that a circle of radius 2 can be written in rectangular form by x squared plus y squared equals 4. To graph this, we have to solve for y, and we get y is equal to plus or minus the square root of 4 minus x squared. If we want to see it in polar form, we realize that the square root of x squared plus y squared is equal to r, so this gives r squared equals 4, and r is equal to 2. We can verify this graphically. Using function mode, we graph y is equal to plus or minus the square root of 4 minus x squared. We see that the calculator has problems when the graph becomes vertical because of the resolution of the screen. Calculators do not do well with vertical lines in function mode. There's nothing that you really can do about that. But when we graph this in polar mode, we get a perfect circle. Note also that we can graph this polar equation using either radian or degree mode. In addition to changing theta min, theta max, and theta step, you must also change the mode from radians to degrees or vice versa. If your R equation involves operations on theta that are not trigonometric, you must be in radian format. And when we use the calculator for calculus purposes, as we will soon do, we must be in radian format as well. In problem number 7, we are given rectangular equations and asked to change them to polar equations using our transformational relationships. In A, we are given that y is equal to 6. Y is equal to r sine theta, which is equal to 6, and therefore r is equal to 6 over sine theta, or 6 cosecant theta. B reads 4x minus 2y minus 1 is equal to 0. We replace x with r cosine theta and y with r sine theta. So we have 4r cosine theta minus 2r sine theta minus 1 is equal to 0. We can factor out an r, and we end up getting r is equal to 1 over 4 cosine theta minus 2 sine theta. Number 7 reads y equals 4x squared. We replace y with r sine theta and x with r cosine theta, and we get r sine theta is equal to 4r squared cosine squared theta. Bringing everything to one side, we have r times the quantity 4r cosine squared theta minus sine theta is equal to 0. Since r does not equal 0, we can say that 4r cosine squared theta equals sine theta, and therefore r is equal to sine theta over 4 cosine squared theta. To get some practice with the calculator, you may want to graph each of these in their own particular mode and show that you get the same graph. In number 8, you are given equations in polar form and asked to change them to rectangular form using the transformational relationships you were given. 8a reads r equals negative 2 cosecant theta. We can write that as r is equal to negative 2 over sine theta, and cross multiplying we get r sine theta equals negative 2. But r sine theta is y, so our answer is y equals negative 2. B reads r is equal to 2 over sine theta plus 3 cosine theta. We cross multiply and get r sine theta plus 3r cosine theta is equal to 2. And that simply gives y plus 3x equals 2, or y equals 2 minus 3x. C reads r is equal to 2 over 1 plus 2 cosine theta. We cross multiply, and utilizing the fact that r cosine theta is equal to x, we get r plus 2x is equal to 2. Since r is the square root of x squared plus y squared, we get the square root of x squared plus y squared is equal to 2 minus 2x. We have a rectangular equation, but we'd like to get this in the form of y equals. So we square both sides and get x squared plus y squared is equal to 4 minus 8x plus 4x squared. And therefore y is equal to plus or minus the square root of 3x squared minus 8x plus 4. Again, you are encouraged to graph these on your calculator in both modes and show that you get the same graph. We will see soon that it is preferable to express equations in parametric form. We can easily do this because we know that x is equal to r cosine theta and y is equal to r sine theta. So in problems 9, A through C, you're asked to change these polar equations to parametrics. In 9a, r is equal to 4, so x is equal to 4 cosine theta and y is equal to 4 sine theta. In b, r is equal to 4 sine theta, so x is equal to 4 sine theta cosine theta, where y is equal to 4 sine theta, or 4 sine squared theta. In C, r is equal to 4 over cosine theta. So x is equal to 4 over cosine theta times cosine theta, which is 4. Y is equal to 4 over cosine theta times sine theta, which is 4 tangent theta. Again, you are recommended to graph these in parametric form and polar form and show that they are the same. A sharp-eyed student may have picked up a discrepancy from the last screen. We'll use 7a as an example. It graphed y equals 6. We know that is a horizontal line and certainly is continuous. There never was a curve that was more continuous. We then changed it to our polar form, r is equal to 6 over sine theta. But that curve is not continuous at certain values of theta. What's going on? The secret is how the curve is generated. Remember that r is the distance from the origin, or pole, up to the curve. When theta is 0 degrees, or 180 degrees, that distance is infinite. It cannot get up to the red horizontal line because it will always be along the x-axis. But when theta is equal to 1 degree, for instance, it will reach the red line. Its distance is 6 over the sine of 1 degree, which is approximately 344. A big number, but it will get there. As theta increases, this distance gets shorter. When theta is equal to 90 degrees, or pi over 2, that distance is exactly 6. The same thing occurs when theta is greater than 90 degrees. The distance starts to increase again. And when theta is equal to 180 degrees, that distance becomes infinite again. So this graphs a line generated right to left. When theta is between 180 degrees and 360 degrees, r will be negative, so the graph will end up repeating itself. As we did with functions and parametric equations, we are interested in finding the slope of a tangent line to a polar graph. The polar graph will be in the form of r is equal to f of theta, and we assume it is differentiable. The key is changing the polar equation to a parametric equation. So x is equal to r cosine theta, which can be written as f of theta cosine theta, and y is r sine theta, which is f of theta sine theta. We are now where we were at in our previous videos, where we have parametric equations describing the curve. The slope dy dx of this differentiable function can be written as dy d theta over dx d theta. Since both y and x are expressed as products, we use the product rule. And therefore dy d theta is f of theta cosine theta plus f prime of theta sine theta. Dx d theta is negative f of theta sine of theta plus f prime of theta cosine theta. I do not recommend that you memorize this formula. You will have y and you will have x. Simply take their derivatives. The slope of our graph will be dy d theta over dx d theta, assuming that dx d theta is not equal to 0 at the point r theta. So now, to find horizontal tangents to polar graphs, we set dy d theta equal to 0, provided that dx d theta does not equal 0. To find vertical tangents to polar graphs, we set dx d theta equal to 0, provided that dy d theta is not equal to 0. If both dx d theta and dy d theta are simultaneously equal to 0, we can make no conclusions about tangent lines. On 10a and b, we're asked to find values of theta for which the polar graph has horizontal and vertical tangent lines, and we want to verify our results graphically. Job 1 is to write the polar equation parametrically. So x is equal to r cosine theta, or 2 sine theta cosine theta, where y is equal to r sine theta, which is 2 sine theta sine theta, or 2 sine squared theta. We start with taking dx d theta, which is a product rule, and we get 2 cosine squared theta minus sine squared theta equals 0. That gives us sine squared theta equals cosine squared theta, or tangent squared theta equals 1, and that makes tangent theta equal plus or minus 1. On the intervals 0 to pi, theta is equal to pi over 4 and 3 pi over 4. We are not ready to make a claim yet about horizontal and vertical tangents because we must first take a look at dy d theta to make sure that it does not equal to 0 at the same places where dx d theta equals 0. We now concentrate on y, which is equal to 2 sine squared theta. That gives us dy d theta is equal to 4 sine theta cosine theta, set equal to 0. Theta is equal to 0, pi over 2, and pi. Since there are no places where dx d theta and dy d theta are simultaneously equal to 0, we conclude that there are vertical tangents at theta is equal to pi over 4 and 3 pi over 4. Horizontal tangents at theta is equal to 0, pi over 2, and pi. The graph of r equals 2 sine theta, where theta runs from 0 to pi, confirms our solution. It is a circle. There are two locations of horizontal tangency, 0 and pi over 2. Pi brings us back to the same place, and vertical tangencies are at theta equals pi over 4 and 3 pi over 4. 10b asks to find the values of theta where there are horizontal and vertical tangent lines to the polar graph r equals 2 quantity 1 minus sine theta, where theta runs from 0 to 2 pi, and to confirm graphically. This problem is a lot of work, and your work must be organized to get it correct. Our first job is to write the polar equation parametrically. We know that x is equal to r cosine theta, so x is equal to 2 quantity 1 minus sine theta times cosine theta. We know that y is equal to r sine theta, and therefore y is equal to 2 quantity 1 minus sine theta times sine theta. We will work with the x's first. First multiply, and we get x equals 2 quantity cosine theta minus sine theta cosine theta. We then take dx d theta, getting 2 quantity negative sine theta minus quantity negative cosine squared theta minus sine squared theta. In the next step, we utilize the fact that cosine squared theta is equal to 1 minus sine squared theta. And that gives us 2 quantity negative sine theta plus 2 sine squared theta plus 1. Finally, we have this in a factorable form, 2 quantity 2 sine theta plus 1 times the quantity sine theta minus 1, and we're going to set that equal to 0. For 2 sine theta plus 1 equals 0, that gives us sine theta equals negative 1/2, and theta is equal to 7 pi over 6 and 11 pi over 6. For sine theta equals 1, we get theta is equal to pi over 2. So there are 3 candidates for vertical tangency. The thing that makes this problem hard is that even if you were just asked for vertical tangency, you still have to do the horizontal tangency to see if there are any values of theta that appear in both. So we have y is equal to 2 quantity sine theta minus sine squared theta. Taking the derivative, we get 2 times the quantity cosine theta minus 2 sine theta cosine theta. And now we can write that as 2 cosine theta times the quantity 1 minus 2 sine theta. Setting that equal to 0, we get cosine theta equals 0, and theta is equal to pi over 2 and 3 pi over 2. Sine theta equals 1/2, and theta is equal to pi over 6 and 5 pi over 6. So there are 4 candidates for horizontal tangency. However, we now see that the value of pi over 2 is in both, so that is a point where we cannot determine what is going on. But there are vertical tangencies at 7 pi over 6 and 11 pi over 6, horizontal tangencies at pi over 6, 5 pi over 6, and 3 pi over 2. Our graph confirms the fact that there are 3 horizontal tangents and 2 vertical tangents. Theta is equal to pi over 2 is a cusp point. The name of this curve is called a cardioid because it is heart-shaped. Finally, we end up with a concept called tangency to the pole. If r is equal to f of theta, which is equal to 0, at theta equals alpha, and f prime of alpha does not equal 0, then we say that the line theta equals alpha is tangent to the pole. In 11a, we are interested in values of theta where r equals 4 cosine 3 theta is tangent to the pole. We set 4 cosine 3 theta equal to 0. The best way of solving that is realizing that for a cosine to equal 0, the angle must be pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, 9 pi over 2, or 11 pi over 2. Therefore, theta equals pi over 6, pi over 2, 5 pi over 6, 7 pi over 6, 3 pi over 2, and 11 pi over 6. To confirm, we take f prime of theta and get negative 12 sine of 3 theta, and realize that f prime is not equal to 0 at any values in that list. So we see the lines for the 6 lines where we have tangency at the pole. We see the graphic confirmation. In reality, pi over 6 and 7 pi over 6 are the same line, as are pi over 2 and 3 pi over 2, and 5 pi over 6 and 11 pi over 6. So in reality, there are 3 lines of tangency to the pole. 11b reads r equals 3 quantity 1 minus sine of 2 theta. To find tangency at the pole, we set that expression equal to 0 and get sine of 2 theta is equal to 1. The angle whose sine is equal to 1 is pi over 2 and 5 pi over 2. So 2 theta equals pi over 2 and 5 pi over 2, and theta is equal to pi over 4 and 5 pi over 4. We then take f prime of theta and get negative 6 cosine of 2 theta. And we see that f prime of pi over 4 and f prime of 5 pi over 4 is equal to 0. So technically there are no tangents at the pole. This is not confirmed graphically. We graph the expression r equals 3 quantity 1 minus sine of 2 theta. And we also graph theta is equal to 5 pi over 4 and pi over 4. And we see that it appears to be tangent at the pole. The answer to this is that if f of theta equals 0 and f prime of theta is not equal to 0, we definitely have tangency at the pole. However, if f of theta equals 0 and f prime of theta is equal to 0, we may have tangency at the pole. That is what is happening here, and we do indeed have tangency at the pole.